Let's learn about OSPF neighborship formation in a broadcast network. In the previous lesson, we configure OSPF on all four routers and we was able to verify the routers became the neighbors and synchronize their link state databases. In this lesson, we will find out how the routers form the neighborship. In order to do that, we will put the Wireshark captures on these three links which belong to the broadcast network in area 0, then restart all the routers. After that, we will analyze the Wireshark captures to understand the neighborship formation process. Here is the capture on the link between router 1 and switch 1. Let's get to know the OSPF packets sent among the routers during the neighborship formation process. Then we will analyze the detail. As you can see, the routers first send the hello packets, then the database description packets. Next, they send the link state request packets. After that, the routers send the link state update and then link state acknowledge package, which completed the neighborship formation process. Finally, the routers send the hello package again and again to check their neighbor status. Let's get started with the analysis. To make it simple, we only analyze the activities between router 1 and router 2. As you may know, when the routers are starting and OSPF processes have not been started, from OSPF perspective, these routers are in down state and they will be transitioned into the init state as soon as the OSPF processes start and the routers send their first hello package to discover the neighbors. Here is the first hello packet sent by router 1. As you can see, it's sent from router 1 to the multicast address 224.0.0.5. In the OSPF header, we see that it is a hello packet and it identifies the router ID and it is for area 0 and the checksum is correct and there's no authentication information configured. In the OSPF hello packet detail, we see that it identifies the subnet, the hello interval, the dead interval, and especially it provides the router priority. And in this case, it still does not know about the DR or the BDR, and it does not have any information about the neighbor. And here is the hello packet sent by router 2. It provides the similar information. However, in this case, the router priority is 1 and router 2 does not have any information about the DR or BDR and its neighbors. As you can imagine, upon receiving the discover hello package from the neighbors, router 1 and router 2 will respond with their hello package, including the active neighbors in the hello packet detail. The routers will be transitioned into two-way states as soon as they receive the hello package from the neighbors, listed them as active neighbors. Here is a hello package that router 2 received from router 1. As you can see, router 1 listed router 2 and router 3 are the active neighbors, which allow router 2 to transition into two-way state. Similarly, here is a hello packet that router 1 received from router 2, and in this case, router 2 listed router 1 and router 3 are the active neighbors, which allow router 1 to transition into two-way state. As you may also notice, the more important information is that router 2 also identifies router 1 is a DR and BDR, which allows both router 1 and router 2 to advance to the next stage. If neither router 1 nor router 2 is elected as DR or BDR, the two routers will only become the neighbors and stay at the two-way stage. Now routers advance to the extart stage. At this stage, the two routers try to become the master to control the database synchronization process. Per OSPF design, the router with higher router ID of the two neighbors decides which router becomes the master. As you can see, both router 1 and router 2 try to become the master. However, router 2 will decide since it has higher router ID. After deciding which router is the master, the two routers advance to the exchange state to exchange the database description packets to describe their local link state databases. Here is the database description package that router 1 received from router 2. As you can see, router 2 is the master, and it tells router 1 that it has the router LSA and summary LSAs. And here is a database description package that router 2 received from router 1. And as you can see, router 1 is not the master, and it tells router 2 that it has the router LSA and network LSAs. After exchanging the database description package, the two routers identify the missing information and advance to the loading stage to synchronize their link state databases. At first, the two routers start sending the link state request. Here is the link state request that router 2 sent to router 1. As you can see, router 2 requests the router LSAs and the network LSAs from router 1. And here is the link state request that router 2 received from router 1. As you can see, router 1 requests the router LSA and the summary LSAs from router 2. Upon receiving the link state request, the two routers will respond with the link state updates back to the neighbors. Here is the link state update package that router 2 sent to router 1. As you can see, it updated router 1 with its router LSAs and summary LSAs. And here is a link state update package that router 1 sent to router 2. As you can see, router 1 updated router 2 with its router LSAs and network LSAs. After updating these link state databases with the LSAs sent from the neighbors, the routers send the link state acknowledge package. Here is the link state acknowledge package that router 2 sent to router 1. This package tells us that router 2 confirmed it got the router LSA from router 1. And here is a link state acknowledge packet that router 1 sent to all the neighbors. The reason is that router 1 is the DR. In this case, router 1 confirmed that it got the two router LSAs. The loading continues until the link state databases of all routers are in sync. After the link state databases are fully loaded among the neighbors, The routers continue to send the hello packets at each hello interval. In this case, the hello interval is 10 seconds, and the hello package contains the router ID, the area is 0, and the priorities, and the DR is router 1, and the BDR is router 3, and the active neighbors. Any change in the network, or if the routers do not hear back from the neighbors within the dead interval configured by the neighbors, and in this case it is 40 seconds, an update will be triggered. Here are the keynotes for this lesson.